Happy Monday guys, welcome to today's worked exam answer video, where today I'm having a look at a catalysis question which comes under the transition metal topic within the AQA specification. And the reason why I've chosen to do this particular question today is because I imagine that a lot of you in year 13 are now getting to this point where you're covering this in lessons at school or college. And I also, want to show that whilst for a lot of the inorganic content, including transition metals and things like group 2 and group 7, there are lots of sort of facts we need to know, lots of things we just have to remember, but therefore where there are opportunities for us to be able to work things out, like the equations that were being asked for in this particular question, I feel like it's important that I share how we can work those things out and how they are derived, so that if you are not confident in your ability to remember the equations, or you know that kind of rote learning things is your downfall, then hopefully this will help, because I'm going to show you that you don't need to rote learn the equations. Obviously there's other parts of this question as well that we'll have a look at, but I guess that felt really important for me to go through with you. So in this particular question, we're looking at how iron 2+ ions can catalyse the reaction between these peroxide disulfate ions, which are these, the S2O8 2-, and iodide ions in aqueous solution. So this is an example of a homogeneous catalysis because the iron ions, which will also be in solution, are in the same phase as our reactants, which are ions in solution. And initially we've got to think about why the reaction is slow before the catalyst is added. And this is commonly asked in relation to this example, but also other catalysis examples as well. And we've got two negatively charged ions here that are trying to react with one another. So we are going to get repulsion between those ions, and therefore the activation energy is going to be very high. The advantage of using iron 2+ ions is that they are positive. So what the Fe2+ ions are going to do is they're going to react with one of the negative ions first, which is the peroxide disulfate ones, and that is going to then generate an intermediate ion species, which is Fe3+, and then those Fe3+ ions are going to then pick off the iodide ions, and again positive Fe3+ ions reacting with a negative iodide ion, the activation energy is going to come down. So it's important that we appreciate why this reaction is slow and be able to explain that, and of course I'll put that onto the paper in a second. And then the bit that I guess lots of students will just go about remembering, and I don't want to say that that's not the right way to do it, but I had to rely on my memory when I did my own A-level because I wasn't aware of how certain things worked, how to derive equations like this one, and that put a lot of pressure on me in exams to be able to pull all of these sort of equations and colours and facts out of my head. And so therefore it is important to me to show you that you don't have to rote learn certain things. So the two equations that we are going to be writing are showing how the Fe2+ reacts with these peroxide disulfate ions first, and then how the Fe3+ ions generated would react with the iodide ions. So that's what we are going to be having a look at in this question. That's what I'm going to show you how to do. So first and foremost, explain why this reaction is slow. There are two negatively charged ions. Reacting. These will repel one another. Thus, the activation energy is very high. And although it doesn't ask us in this question, if it then says, well, why therefore are Fe2+ ions a good catalyst to use? Two reasons. One, they're positively charged, so you have your positive ion and negative ion reacting, brings your activation energy down. Two, iron being a transition metal, exists in variable oxidation states. Okay? Now, the two equations that we need to write, I'm going to start by just writing them out from memory, and then I'm going to show you how we can derive them. So I guess, yeah, relying on just rote learning, you can just remember that it's going to be two Fe2 plus ions reacting with the S2O8 2 minus ions, and that gives us our sulfate ions, the SO4 2 minuses in the products, and then generates Fe3 plus ions. And then the second equation that you would be kind of regurgitating, I suppose, would be two Fe3 plus ions reacting with the two iodide ions to give us the iodine, and regenerating those Fe2 plus ions. So because the Fe2 plus ions are acting as a catalyst, whilst we are temporarily changing the oxidation state of those iron ions, we have to regenerate the catalyst, because catalysts are not permanently changed in a reaction. That is one of the key things that defines catalysts. If we didn't reform them, then they would be acting as a reactant rather than a catalyst. And so those are the two equations that you can just remember. Now, what you should find when you've written these is that, because, as I said, the iron 2 plus ions are a catalyst, they should cancel. We also need to have the intermediate ions also cancelling, and then that should give us our overall equation, which it does. So those are the two equations that would be 4 marks for the first part of this question. However, if we think about how we can derive what I'm going to call equation 1 and equation 2, what we, I guess, would need to be aware of is that each of these equations is a redox equation in its own right. So in just reaction 1, we have both oxidation and reduction occurring, and in reaction 2, we have both oxidation and reduction occurring. So whilst I have remembered these equations off by heart now, probably just because I've done them so many times, there is another example of catalysis, the autocatalysis example involving Mn2 plus ions, and I don't know those equations to show how the Mn2 plus ions catalyse that reaction, but I know I can figure them out using the same sort of ideas I'm going to show you here. So in reaction 1, we've got Fe2 plus ions, and the only other oxidation state that we need to be aware of for iron is our Fe3 plus ions. So when we think about transition metals being used as catalysts, the fact they have variable oxidation states is key. So the other oxidation state for iron is +3, so that is the process that would be happening. We would be oxidizing those Fe2 plus ions to form our Fe3 plus ions. We can also then write a half equation for the S2O8 2 minus ions, becoming the 2 lots of SO4 2 minus ions. Now, the 2 in there is balancing our sulfurs, and it's also therefore balancing our oxygens. So the only thing that isn't balanced in this half equation is the charges, because the balancing 2 here gives us a charge of 4 minus on this side. So we're going to need to add 2 electrons on the left side. And we can see therefore that we've got both oxidation and reduction. And this explains why the Fe2 plus ions choose to react with the peroxide disulfate ions first. The Fe2 plus couldn't react with the iodide ions because that would be 2 lots of oxidation. And it always has to be oxidation and reduction because we need electrons to be lost from somewhere so that they can be gained somewhere else. Now, from there, as with, I guess, writing any redox equation, we've got to have the same number of electrons on both sides. So I'm going to have to multiply everything in the top equation by 2. And then when I go to join those together, we will get the equation that I wrote out from memory. 2 Fe2 plus ions reacting with the S2O8 2 minus ions. I'm not going to write the electrons because they're going to cancel. That's going to give us 2 Fe3 plus and 2 SO4 2 minus. And we can see there that we've got everything that I wrote here. Now, it's the same for equation 2. In equation 2, we have to use up the intermediate Fe3+ ions that we've just made. And so if we write a half equation for that, they're going to need to gain an electron to reform the Fe2+ ions. And the iodide ions need to become iodine atoms so that we can get our iodine molecules, because iodine is diatomic. Now, again, the 2 here is balancing the iodines. There's no other atoms, so in order to finish this half equation, I just need 2 electrons. So I would hope that you're comfortable with writing half equations and redox equations, and if you are, then this might be really helpful for you. Now again, in order to join these together, my electrons need to be balanced. So again, it is the iron half equation that I need to double up. And then when I join those together, again, we will see that that is going to give us the equation that I regurgitated earlier from memory. But hopefully this shows that you don't need to rely on your memory for the whole equations. Now, obviously, in order to get started with these, we are going to need to, well, I guess it would make sense to remember that the Fe2+ starts by reacting with the S2082-, but even if you couldn't remember that, or you forgot it on the day, you wouldn't be able to have the Fe2+ reacting with the I-, because your electrons would be on the same side of your half equations, so that wouldn't work. So I do think that it's very doable to not rote learn these and to work them out. Obviously working them out is a bit more of a job in the actual exam on the day, but I do think there's a lot of benefits to being able to work them out like that. Hopefully that all makes sense for that question, but if anybody isn't certain as to what I've done there, please do let me know. Okay, then it says give a reason why the Zn2+ ions do not catalyse the reaction in part B. So when we think about our transition metals, they make really good catalysts because of the fact that they exist in variable oxidation states, and we can just flip between the two. We can turn our iron 2+ into iron 3+ and easily turn it back again. We can oxidise and then we can reduce. Zinc, even though it lies in the D block, zinc is not a transition metal. The Zn2+ ions do not have an incomplete D sublevel because zinc as an atom has the configuration of argon and everything that argon has. That's me cheating a little bit there. And then the configuration would be 4s2 3d10. And so when we then form Zn2+ ions, again the configuration would be everything of argon, and then we lose the 4s2 first. That is the rule for the D block elements. So the zinc ions would be Ar square brackets 3d10. Now that means it is not a transition metal because it does not have an incomplete D sublevel, and if it is not a transition metal, it will not exist with variable oxidation states, and that is what is needed here. We can't change the Zn2+ to any other oxidation state and turn it back again because it doesn't exist in any other oxidation states. So I'm going to finish this off by saying Zn2+ ions have a full 3D sublevel so zinc does not exist with variable oxidation states. And apologies if you're wondering why it sounds like I'm in monsoon rain, my window cleaner has just shown up. So it's important that we make the connection to the fact that it's not a transition metal, but it isn't just enough to say it's not a transition metal. I think it's important that we understand why, and that we show that we understand why that is true, because it doesn't have an incomplete D sublevel, or it has a full 3D sublevel, and the bit that makes it, or the bit, sorry, that makes the transition metals be brilliant catalysts is they have those variable oxidation states, and obviously therefore zinc does not have those. I hope that that's been somewhat useful. If you'd like me to do something similar with the manganese autocatalysis example, I absolutely can do. I think I've actually got that planned to do in one of my upcoming videos. But as always, questions very much welcome, and so are requests. I hope you have a great week, guys, and I will catch you soon.